Hello there, and welcome to this quiet corner where science unfolds without hurry and the most profound mysteries of our universe are allowed to breathe. Tonight, we're not rushing toward answers. We're taking a slow walk through one of the strangest, most fundamental limits that governs everything around us. A speed limit that isn't posted on any highway, isn't enforced by any authority we can see, and yet shapes the very fabric of reality itself. What if I told you that there's a cosmic speed limit built into the universe? Not just a suggestion, not just a practical limitation, but an absolute, unbreakable boundary that nothing, absolutely nothing, can cross. And what if I told you that this limit isn't arbitrary, isn't some cosmic coincidence, but is woven so deeply into the structure of space and time that without it, reality, as we know it, would simply collapse. This is the story of light speed. Not just how fast light travels, but why that speed represents something far more profound than just electromagnetic radiation zipping through space. It's the story of a universal constant that connects energy to mass, links space to time, and creates the very framework within which cause and effect can exist at all. Before we dive into the strangeness of it all, I'd love to know where you are right now as you're listening to this. What time is it where you are? Are you winding down for the night? Or perhaps letting your mind wander during a quiet moment? Wherever you are, whenever it is, I'm glad you're here for this journey. If this kind of gentle exploration into the deepest questions of physics appeals to you, I'd be grateful if you considered subscribing. It helps this little signal reach other curious minds who, like you, find wonder in the way the universe works. Now, settle in. Maybe dim the lights if you can, because what we're about to explore will change how you see every photon of light that reaches your eyes, every second that ticks by on your clock, and every step you take through the space around you. Let's begin with something that seems simple but isn't. Light travels at approximately 792,458 meters per second in a vacuum. That's about 186,282 miles per second if you prefer. It's fast, incomprehensibly fast. In the time it takes you to blink, light could travel around the Earth's equator more than 7 times. In a single second, it could make the journey from Earth to the Moon and back again with time to spare. But here's where it gets interesting. That speed isn't just fast, it's special. It's the speed at which massless particles must travel. Not can travel, must travel. Light doesn't have a choice in the matter. Photons, the particles of light, are born moving at this speed and can never, under any circumstances, slow down or speed up. They exist only in motion, only at this precise velocity, only at the cosmic speed limit. And here's the truly strange part. Nothing else can join them there. Nothing with mass can ever reach this speed, no matter how much energy you give it, no matter how hard you push. As you approach light speed, something fundamental happens to matter itself. It becomes harder and harder to accelerate, as if the universe is gently but firmly saying, no, you cannot pass this threshold. This isn't just a practical limitation, like running out of fuel in your car. It's not that we haven't built powerful enough engines or discovered the right technology. The prohibition is written into the mathematical structure of reality itself. The equations that govern space, time, energy, and mass all conspire to create this absolute barrier. But why? What makes this particular speed so special that the entire universe seems organized around it? The answer lies not in light itself, but in something much deeper. Something that touches every aspect of how reality is constructed. To understand this, we need to step back and look at what happened in 1905, when a young patent clerk named Albert Einstein was thinking about some very strange experimental results. Scientists had been trying to measure the speed of light using increasingly sophisticated equipment, expecting to find that it varied depending on how fast the Earth was moving through space. After all, if you're on a train moving forward and you throw a ball in the direction the train is travelling, the ball's speed relative to the ground is the train's speed plus the ball's speed. Simple addition. But light didn't behave this way. No matter how fast the Earth was moving, no matter what direction it was travelling, light always measured the same speed. Always. This was deeply troubling because it violated everything scientists thought they knew about motion and velocity. Einstein looked at this puzzle and made a radical proposal. What if light speed isn't just a property of light? What if it's a property of space and time themselves? What if the speed of light represents something fundamental about the structure of the universe, a kind of cosmic constant that defines the relationship between space and time? This insight led to special relativity, and with it, a complete revolution in how we understand reality. Einstein showed that space and time aren't separate, independent things. They're woven together into a single fabric called spacetime. And the speed of light? It's the rate at which information, energy, and causality itself can propagate through this fabric. Think of it this way. Imagine space-time as a vast ocean, and events as waves moving across its surface. The speed of light is like the maximum speed at which any wave can travel through this medium. It's not that light is special in and of itself. It's that light travels at the fundamental speed limit of the universe, the maximum rate at which cause and effect can spread from one point to another. This has profound implications. It means that when something happens here, the effects of that event cannot instantly influence something happening there. There's always a delay, a finite amount of time it takes for the influence to propagate. And that maximum speed of propagation is the speed of light. But here's where it gets truly mind-bending. As objects approach this cosmic speed limit, space and time themselves begin to behave strangely. Time slows down for the moving object. Distances contract. Mass appears to increase. These aren't just theoretical curiosities. They're real, measurable effects that we observe every day in particle accelerators around the world. At Fermilab, scientists routinely accelerate protons to 99.97% of light speed. These particles are moving so fast that their behavior becomes dominated by relativistic effects. As they approach the speed of light, something remarkable happens. No matter how much more energy the scientists pump into the accelerator, the particles don't get significantly faster. Instead, they get more massive. The energy goes into increasing their effective mass rather than their speed. It's as if the universe has a built-in mechanism that prevents anything with mass from reaching light speed. The closer you get, the more energy it takes to go even a tiny bit faster. To actually reach light speed would require infinite energy, which is physically impossible. The speed of light becomes an asymptotic limit, something you can approach but never reach. This leads us to one of the most famous equations in all of physics. E equals mass squared. Energy equals mass times the speed of light squared. Notice that the speed of light appears in this equation not as the speed of light per se, but as a conversion factor between mass and energy. It tells us that mass and energy are fundamentally the same thing, viewed from different perspectives. And the speed of light squared is the exchange rate between them. Because the speed of light is such a large number, and its squared in reactions release so much power, why stars can Einstein's equation, even tiny amounts of mass, correspond shine for billions of years, and why the universe itself is to enormous amounts of energy. This is why nuclear is something even stranger, lurking in such an energetic place. But their energy approaches infinity, not equations. As an object approaches light speed, its very large number, but actual mathematical infinity. This is the universe's way of saying that light speed is absolutely forbidden for anything with mass. It's not just difficult to reach, it's impossible in principle. Only massless particles can travel at light speed, and they must travel at light speed. They have no choice in the matter. Photons, the particles of light, exist only in motion, only at this cosmic speed limit. They cannot slow down, cannot speed up, cannot rest. They are creatures of pure motion, ambassadors from the realm of the speed limit itself. This creates a strange duality in the universe. There are things that can never reach light speed, no matter how much energy they have. And there are things that can never travel at any speed other than light speed. The speed of light becomes a kind of boundary between two fundamentally different types of existence. In particle accelerators like the Large Hadron Collider, scientists push protons to incredible energies, 6.5 trillion electron volts each. These particles are moving at about 99.9999% of light speed. They're traveling at roughly 3.1 meters per second, slower than light itself. That might not sound like much of a difference, but it represents an enormous gap in terms of the physics involved. To appreciate just how difficult it is to approach light speed, imagine accelerating something from rest to 99% of light speed. That takes a tremendous amount of energy. To go from 99% to 99.9% takes even more energy. To go from 99.9% to 99.99% takes vastly more energy still. Each additional 9 in the decimal expansion requires exponentially more energy than the last. The energy requirements grow without bound, approaching infinity as the speed approaches light speed. This isn't a limitation of our technology. It's a fundamental feature of the universe. Even the most energetic cosmic rays, particles accelerated by processes we don't fully understand involving supercatastrophes, never exceed light speed. They novas and black holes, another most energetic cosmic ray particle ever detected, 320 quintillion electron volts of particle, carried the oh my god energy. It was moving so close to light speed that in a year-long race with light itself, it would have lost by mere thousandths of the width of a human hair. But it was still slower than light. Nature herself, with all the violent energy of exploding stars and colliding galaxies, cannot break this speed limit. The universe seems to have built-in safeguards, mathematical constraints, that preserve this fundamental boundary no matter what forces are brought to bear against it. But why is this boundary so important? What would happen if it could be violated? The answer touches on one of the deepest principles in physics: causality. The idea that cause precedes effect, that events happen in a logical order, that the universe makes sense. If information could travel faster than light, it would be possible to send signals into the past. This isn't science fiction speculation. It's a direct mathematical consequence of the equations of relativity. Faster than light travel would allow you to violate causality, to create logical paradoxes, to affect events before their causes occurred. The speed of light, then, isn't just about light. It's about the logical structure of reality itself. It's the universe's way of maintaining order, of ensuring that effects follow causes, that time flows in one direction, that the story of existence unfolds in a coherent way. This brings us to one of the most beautiful and strange aspects of this cosmic speed limit. It doesn't just govern motion through space, it governs the flow of time itself. As you approach light speed, time begins to slow down relative to stationary observers. This isn't just a theoretical prediction, it's something we can measure, something that affects particles created in cosmic ray collisions high in Earth's atmosphere. Consider muons, unstable particles that should decay in about 2.2 microseconds. At that lifetime, even travelling at nearly light speed, they should only make it about 600 meters before disappearing. But muons created by cosmic rays, 10 kilometers up in the atmosphere, regularly reach Earth's surface. How is this possible? The answer lies in time dilation. Because these muons are travelling so close to light speed, time passes differently for them. From normal 2.2 microsec their perspective, they live there on lifetime. But from our perspective on Earth, their clocks are running slow. What seems like 2.2 microseconds to them corresponds to about 90 microseconds to us. This extended lifetime allows them to travel the full distance from the upper atmosphere to the ground exotic effect that happens to strange particles. Evrid. This isn't just an GPS satellite orbiting Earth experiences time dilation. The satellites are moving fast enough and are far enough from Earth's gravitational field that their clocks run slightly faster than clocks on the surface. Without correcting for this relativistic effect, GPS would accumulate errors of several kilometers per day. The speed of light limitation and the time dilation it creates is built into the technology you might be using to navigate to work tomorrow morning. But perhaps the most mind-bending consequence of the cosmic speed limit appears when we consider what happens at the extreme end of the scale. Black holes represent regions where gravity becomes so intense that not even light can escape. The event horizon, the boundary beyond which nothing can return, is defined precisely by the speed of light. Within the event horizon, all paths lead inward. Even light, travelling at the cosmic speed limit, cannot climb out of the gravitational well. The speed of light, which represents the maximum rate at which anything can move through spacetime, becomes insufficient to overcome the warping of spacetime itself. Black holes exist precisely because nothing can exceed light speed. If faster than light travel were possible, black holes, as we understand them, could not exist. This creates a fascinating connection between the smallest scales of quantum mechanics and the largest scales of cosmology. The same speed limit that governs the behavior of individual photons also determines the nature of the most massive objects in the universe. It's as if the cosmos has a single, unifying principle that operates at every level of reality. Even in the quantum realm, where particles can seem to behave in impossible ways, the speed of light maintains its authority. Quantum entanglement allows two particles to be correlated in ways that seem to violate locality. Measure one particle's spin, and you instantly know the spin of its entangled partner, no matter how far away it is. This appears to involve faster than light influence, but appearances can be deceiving. The key insight is that while the correlations are instantaneous, no information actually travels between the particles. You cannot use quantum entanglement to send a message faster than light. The universe seems to have found a way to allow these strange quantum correlations while still preserving the fundamental speed limit for information transfer. Causality remains intact, even in the quantum world. This leads to a profound realization about the nature of reality. The speed of light isn't just a speed, it's a fundamental constant that defines the structure of spacetime itself. It determines how energy relates to mass, how space relates to time, how cause relates to effect. It's woven into the mathematical fabric of the universe so deeply that changing it would unravel reality as we know it. In particle accelerators around the world, scientists have pushed matter to within a fraction of a percent of light speed, and every experiment confirms the same thing. The closer you get to light speed, the more energy it takes to go even slightly faster. The universe resists, not through any physical force we can point to, but through the very structure of spacetime itself. The equations of special relativity predict that as an object approaches light speed, its mass effectively becomes infinite, requiring infinite energy to reach that final threshold. This isn't a limitation of our technology or our understanding. It's a fundamental feature of how mass, energy, space, and time are related to each other. The mathematics doesn't just describe this behavior, the mathematics is this behavior embedded in the deepest levels of physical law. Scientists have wondered whether there might be particles that naturally travel faster than light, hypothetical entities called tachyons. The mathematics of relativity doesn't forbid them outright, but it makes them deeply problematic. Tachyons would have imaginary mass, would speed up when they lose energy, and would create causality violations that lead to logical paradoxes. While we cannot definitively prove that tachyons don't exist, every search for them has come up empty, and most physicists suspect that some deeper principle prevents their existence. The speed of light stands as a monument to the deep order underlying the apparent chaos of the universe. In a cosmos filled with violence and randomness, with exploding stars and colliding galaxies, with quantum uncertainty and cosmic expansion, this one number remains absolutely constant. Light from the most distant galaxies, photons that have been travelling for billions of years across an expanding universe, arrive at our telescopes at exactly the same speed as light from a flashlight in your hand. This constancy isn't just a curious fact, it's what allows the universe to be comprehensible at all. If the speed of light varied from place to place or time to time, the laws of physics would become inconsistent. Chemistry would break down. Stars couldn't shine steadily. Life, which depends on the reliable behavior of atoms and molecules, probably couldn't exist. The speed of light emerges as something far more profound than just the speed at which electromagnetic radiation travels. It's the rate at which reality itself unfolds, the tempo at which the universe plays its grand symphony of existence. Every photon carries within it this fundamental rhythm, this cosmic heartbeat that sets the pace for everything from atomic transitions to galactic evolution. When you look at a star tonight, the light entering your eyes has been traveling at this cosmic speed limit, carrying information across vast distances and enormous spans of time. Each photon is a messenger from the past, a carrier of causality, a tiny embodiment of the speed limit that shapes everything. And in receiving that light, in the simple act of seeing, you're participating in the grand dance of spacetime itself, governed by this strange and beautiful universal constant that nothing can exceed. There's something almost poetic about how the universe enforces this limit. It doesn't use force in any way we might recognize. There's no cosmic police officer standing guard at the speed of light checkpoint. Instead, the prohibition emerges from the very geometry of spacetime itself, from the mathematical relationships that define how reality behaves at its most fundamental level. Consider what happens when we try to understand this geometrically. In our everyday experience, space has 3 dimensions and time flows separately. But Einstein showed us that this separation is an illusion. Space and time are woven together into a 4-dimensional fabric, where the speed of light plays a very special role. It's the conversion factor between space units and time units, the exchange rate that allows us to treat space and time as aspects of a single entity. In this 4-dimensional space-time, the speed of light isn't really a speed at all. It's more like a fundamental geometric property, similar to how the ratio of a circle's circumference to its diameter gives us pi. Just as pi emerges naturally from the geometry of circles, the speed of light emerges from the geometry of space-time. It's built into the structure of reality itself. This geometric understanding helps explain why the speed limit is so absolute. When you try to accelerate a particle to light speed, you're not just fighting against some external resistance. You're pushing against the very shape of space-time, against the mathematical relationships that define what it means for events to be connected by cause and effect. The deeper you look into this, the more mysterious it becomes. Why should space-time have this particular geometry? Why should the universe be structured in a way that creates this specific speed limit? These questions take us to the edge of what physics can currently answer, to the boundary between what we know and what we wonder about. Some physicists have speculated that our universe might be just one of many possible universes, each with different values for their fundamental constants. In some of these hypothetical universes, the speed of light might be different, or might not exist at all as a meaningful limit. But if such universes exist, they would likely be very different from ours. The delicate balance of forces that allows atoms to form, stars to shine, and complexity to emerge might not hold in a universe with different fundamental constants. The speed of light, then, might not be arbitrary. It might be one of the conditions necessary for a universe that can support structure, information, and ultimately, observers like us who can contemplate these questions. This doesn't mean the universe was designed for us, but it might mean that only universes with certain properties can give rise to beings capable of understanding physics. But let's return to the strangeness of our own universe, where this speed limit creates some truly mind-bending effects. One of the most profound is the way it connects space and time through what physicists call the light cone. Imagine every event in space-time surrounded by an expanding sphere of light. This sphere defines what can influence that event, and what that event can influence in return. Events inside your past light cone can affect you because light or other signals from those events have had time to reach you. Events outside your past light cone cannot affect you because not even light has had time to travel from there to here. Similarly, you can only influence events within your future light cone, events where light from your location has had time to arrive. This creates a beautiful structure in spacetime where causality is preserved by geometry. The speed of light doesn't just limit how fast things can move, it defines the very meaning of cause and effect, creating a logical architecture that prevents paradoxes and maintains the coherence of physical law. The implications ripple through every corner of physics. In quantum mechanics, particles seem to exist in multiple states simultaneously until measured. But even these quantum effects respect the speed of light limit. While quantum correlations can appear instantaneous across vast distances, the actual information about these correlations cannot be transmitted faster than light. The universe seems to have found a way to allow quantum strangeness while still preserving causality. In cosmology, the speed of light creates horizons beyond which we cannot see. The cosmic microwave background radiation, the afterglow of the Big Bang, represents light that has been travelling toward us for nearly 14 billion years. Beyond that horizon lies a region of the universe that remains forever hidden from us. Not because there's nothing there, but because light from those regions hasn't had time to reach us yet. This creates a profound limitation on knowledge itself. There are parts of reality that we can never observe, not due to technological limitations, but because of the fundamental structure of spacetime. The speed of light doesn't just limit motion and causality, it limits what we can know about the universe we inhabit. Yet paradoxically, it's this same limitation that makes knowledge possible at all. If information could travel infinitely fast, if cause and effect could operate without delay, the universe might be so chaotic that no stable patterns could emerge. The speed of light creates islands of stability in spacetime, regions where events can unfold in an orderly fashion, where the past can be distinguished from the future, where memory and prediction become meaningful concepts. Even the way we perceive reality is shaped by this cosmic speed limit. When you look at your hand, you're not seeing it as it is right now. You're seeing light that left your hand a few billionths of a second ago. The delay is tiny, imperceptible, but it's real. Everything you see is slightly in the past because light takes time to travel from objects to your eyes. For distant objects, this delay becomes significant. The sun you see in the sky is 8 minutes in the past. The nearest star beyond our solar system appears as it was over 4 years ago. Distant galaxies appear as they were millions or billions of years in the past. Astronomy becomes a form of time travel, a way of looking back through cosmic history, all made possible by the finite speed of light. This creates a strange situation where the universe reveals its history to us automatically. Every photon carries a timestamp, a record of when it began its journey. The light reaching your eyes right now contains information from across the cosmos and across time, a vast library of the universe's past written in electromagnetic radiation. But perhaps the most profound mystery isn't why nothing can go faster than light, but why light travels at the speed it does. Why 299,792,458 meters per second, and not some other value? This number appears to be arbitrary from our perspective, yet it determines the fundamental character of our universe. The speed of light is related to other fundamental constants through the fine structure constant, a dimensionless number that characterizes the strength of electromagnetic interactions. This constant, approximately 1/137, seems to have no deeper explanation. It simply is what it is, and its value determines how atoms behave, how chemistry works, how stars burn. If the fine structure constant was slightly different, electrons might not bind to nuclei properly, atoms might not form, chemistry might not work, stars might not be able to generate the elements necessary for planets and life. The speed of light, through its connection to other fundamental constants, appears to be fine-tuned for a universe that can support complexity. This doesn't necessarily imply design, but it does suggest that the values of fundamental constants, like the speed of light, might not be as arbitrary as they appear. Perhaps there are deeper principles, not yet understood, that determine why these constants have the values they do. Perhaps the speed of light is what it is because only a universe with this particular speed limit can give rise to observers capable of measuring it, or perhaps we're asking the wrong question entirely. Instead of wondering why nothing can go faster than light, maybe we should ask why anything goes as slowly as light does. From the perspective of a photon, if photons could have perspectives, the journey from one side of the universe to the other would be instantaneous. Time dilation becomes infinite at light speed, compressing any journey, no matter how far, into a single moment. From this view, the speed of light isn't fast at all. It's the fundamental rate at which events can be connected across spacetime, the basic tempo of causality itself. Everything else, all matter with mass, all the particles and objects and beings we're familiar with, travels slower than this fundamental rate. We live in the slow lane of the universe, forever excluded from the realm of pure light speed existence. This perspective reveals something beautiful about the nature of light itself. Photons exist in a realm where space and time have different meanings. They connect distant events instantaneously from their own perspective while maintaining causality from ours. They serve as messengers between the slow world of matter and the timeless realm of pure spacetime geometry. The speed of light emerges not as a barrier, but as a bridge, a connection between different aspects of reality. It's the rate at which information flows through the universe, the speed at which the present moment propagates outward from every event, creating the ever-expanding sphere of now that defines our experience of existence. In this light, the cosmic speed limit isn't a restriction, but a gift. It's what allows the universe to have structure, to have causality, to have meaning. It's what makes it possible for patterns to emerge, for complexity to develop, for consciousness to arise and contemplate its own existence. Without this strange speed limit, without this fundamental constant that nothing can exceed, there might be no universe worth understanding at all. And so the speed of light stands as one of the deepest mysteries and most beautiful truths about our reality. It's simultaneously the fastest thing imaginable and the fundamental rate that defines the pace of existence itself. It connects the largest scales of cosmology to the smallest scales of quantum mechanics, ties together space and time, energy and mass, cause and effect. In every photon of starlight, in every electromagnetic wave, in every particle accelerated to near light speed, we see this cosmic constant in action, this strange speed limit that shapes the very possibility of existence. It reminds us that the universe is far stranger and more wonderful than our everyday experience suggests, governed by principles so fundamental that they define what it means for anything to exist at all. When we really start to grasp what this speed limit means, we begin to see that it touches everything, even the most intimate aspects of our existence. The atoms in your body, the neurons firing in your brain as you process these words, the chemical reactions that keep you alive, all of them are governed by electromagnetic forces that propagate at exactly this cosmic speed limit. Think about that for a moment. When you move your hand, the electrical signals travelling along your nerves are constrained by relativistic effects. When atoms in your muscles interact to create motion, those interactions happen through electromagnetic fields that cannot exceed light speed. You are, quite literally, a being constructed from processes that respect this fundamental limit. But there's something even more strange lurking in the details. The speed of light doesn't just limit how fast things can happen, it determines what can happen at all. Consider the structure of atoms themselves. Electrons orbit nuclei not in the neat planetary paths we often imagine, but in quantum probability clouds that are shaped by the interplay between electromagnetic forces and quantum mechanics. The size of atoms, the distances at which electrons can stably exist around nuclei, the energy levels that determine how atoms absorb and emit light. All of these emerge from calculations that include the speed of light as a fundamental parameter. Change the speed of light, and atoms would have different sizes, different properties, different behaviors. Chemistry, as we know it, would cease to exist. This creates a profound interconnection between the cosmic and the microscopic. The same constant that prevents you from traveling to distant stars faster than light also determines, for life, why the sun can burn, steel can form the complex molecules necessary, why water has the properties it does, why carbon daily for billions of years. The speed of light is embedded in the architecture of matter itself. Scientists have discovered this in the most direct way possible, by pushing matter to its limits in particle accelerators. When protons in the Large Hadron Collider reach 99.99999% of light speed, they're not just moving very fast, they're existing in a state where the fundamental relationships between energy, mass, and motion become dramatically visible. These particles have so much kinetic energy that they're thousands of times more massive than they would be at rest. Not heavier in the sense of having more matter, but more massive in the sense of having more inertia, more resistance to acceleration. The energy pumped into them by the accelerator doesn't make them go faster once they approach light speed. Instead, it makes them behave as if they have more mass. This isn't a side effect or a curious anomaly. It's a direct manifestation of the deep relationship between energy and mass that Einstein revealed. Energy and mass are not separate things that happen to be related by a formula. They are the same thing, viewed from different perspectives, with the speed of light squared, serving as the conversion factor between these two aspects of reality. When you hold a flashlight and turn it on, the photons streaming out carry energy, but they have no mass. They exist as pure energy in motion, traveling at the one speed they must travel, the cosmic speed limit itself. They cannot slow down, because slowing down would require them to have mass, which they don't have. They cannot speed up because they're already traveling at the maximum possible speed. They exist in a strange realm between matter and motion, embodying the speed limit itself. This creates one of the most beautiful paradoxes in physics. Light has no mass, yet it carries momentum. It can push on solar sails, exert pressure on comets' tails, even be absorbed by black holes. How can something with no mass carry momentum? The answer lies in the relativistic relationship between energy, momentum, and mass. For massless particles like photons, momentum comes purely from energy, with the speed of light serving as the connecting link. This same relationship explains why nothing with mass can reach light speed. As an object approaches this cosmic limit, more and more of the energy you add goes into increasing its effective mass rather than its velocity. The object becomes harder and harder to accelerate, not because of friction or resistance in any ordinary sense, but because of the fundamental geometry of spacetime itself. It's as if the universe has a built-in mechanism that becomes stronger the closer you approach the forbidden realm of light speed. The mathematics describes this as a Lorentz factor that approaches infinity as velocity approaches the speed of light. But mathematics aside, what this means is that the universe simply won't let you cross this boundary. The resistance isn't external. It emerges from the very relationships that define what mass, energy, and motion mean. Even more remarkably, this isn't just true for particles in accelerators. It applies to everything, everywhere, at all scales. When cosmic rays, the highest energy particles ever observed in nature, streak through space at nearly light speed, they obey exactly the same rules. The oh my god particle, with its almost incomprehensible energy of 320 quintillion electron volts, was still traveling slower than light. Nature herself, with all the violent energy of the cosmos at her disposal cannot violate this speed limit. This suggests something profound about the nature of physical law. The speed of light isn't just a rule that happens to apply in our local region of space and time. It appears to be a universal constant, the same everywhere and everywhen. Light from the most distant galaxies, photons that have been travelling for billions of years across an expanding universe, arrive at our telescopes at exactly the same speed as light from nearby stars. This constancy is what allows astronomy to work at all. When we see light from a distant star, we can be confident that it travelled at a known, predictable speed. This lets us calculate distances, determine ages, map the structure of the cosmos. The speed of light serves as a cosmic measuring stick, a universal standard that remains constant across space and time. But this raises a deeper question. Why should the speed of light be constant? In our everyday experience, speeds are relative. A ball thrown from a moving train travels faster relative to the ground than relative to the train. But light doesn't behave this way. No matter how fast you're moving, when you measure the speed of light, you always get the same answer. This seems to violate common sense, yet it's been confirmed by countless experiments. The resolution of this apparent paradox requires us to abandon some of our most basic intuitions about space and time. Einstein realized that if the speed of light is constant for all observers, then space and time themselves must be flexible. As you move faster, time slows down, and space contracts in just the right way to keep the speed of light constant from your perspective. This isn't just a theoretical curiosity. Time dilation is a real, measurable effect that shows up in the most practical applications. The global positioning system relies on satellites orbiting Earth at high speed. These satellites experience time differently than we do on the ground. Their clocks run slightly faster because they're moving quickly and are farther from Earth's gravitational field. Without accounting for these relativistic effects, GPS would accumulate errors of several kilometers per day. So every time you use GPS to navigate, you're relying on corrections for time dilation caused by the cosmic speed limit. The same fundamental constant that prevents faster than light travel is built into the technology that helps you find your way home. The abstract mathematics of relativity becomes as practical as the directions to the nearest coffee shop. This connection between the cosmic and the mundane appears everywhere once you start looking for it. The light entering your eyes right now, whether from your screen or from a lamp or filtering through a window, has travelled at the cosmic speed limit to reach you. Each photon carries information about its source, encoded in its energy and wavelength, delivered at exactly the maximum speed at which information can travel through the universe. When you see the sun, you're looking about 8 minutes into the past, because that's how long it took light to travel the 150 million kilometers from the sun's surface to your eyes. When you see the moon, you're looking about 1.3 seconds into the past. Even when you look at your own hand, you're seeing it as it was a few billionths of a second ago. The finite speed of light means that now is not a universal concept. Different observers, moving at different speeds, will disagree about what events are simultaneous. This relativity of simultaneity creates some of the strangest consequences of the cosmic speed limit. Events that appear to happen at the same time from one perspective may occur in different orders from another perspective. The universe doesn't have a single, universal timeline. Instead, it has as many timelines as there are observers, all connected by the speed of light. This might seem like an abstract philosophical point, but it has profound implications for the nature of reality itself. If there's no universal now, then the distinction between past, present, and future becomes more subtle than we might have imagined. Some physicists have argued that this means the future already exists in some sense, just as much as the past does. The speed of light doesn't just limit motion through space, it shapes the very meaning of time. Consider what this means for causality. The principle that causes must precede their effects. In a universe where simultaneity is relative, how do we ensure that effects don't precede their causes? The answer lies in the structure of spacetime itself. The speed of light defines what physicists call the light cone, a geometric structure that preserves causality even when simultaneity is relative. Events that can influence each other are connected by paths through spacetime that respect the speed of light limit. Causes can only affect events within their future light cone, the region of spacetime that can be reached by signals travelling at or below the speed of light. This creates a beautiful geometric order that maintains logical consistency even in a relativistic universe. The light cone structure reveals why faster than light travel would be so problematic. If you could send information faster than light, you could potentially send signals into your own past, creating the possibility of paradoxes. You could, in principle, prevent events that have already happened from your perspective. The speed of light limit prevents these logical contradictions by ensuring that all causal connections respect the geometry of spacetime. This is why physicists are generally skeptical about the possibility of faster than light travel, even in science fiction scenarios involving exotic matter or manipulated spacetime. It's not just that we haven't discovered how to do it yet, it's that doing it would threaten the logical consistency of reality itself. The cosmic speed limit isn't just a practical barrier, it's a guardian of rationality, ensuring that the universe makes sense. But the strangeness doesn't end there. The speed of light also determines what we can know about the universe. There are regions of space so far away that light from them hasn't had time to reach us since the beginning of the universe. These regions lie beyond our cosmic horizon, forever hidden from direct observation. The finite age of the universe, combined with the finite speed of light, creates a fundamental limit on knowledge. This observable universe, the spherical region around us from which light has had time to travel since the Big Bang, contains all the information we can ever hope to gather through direct observation. Beyond this horizon, there may be more galaxies, more stars, more worlds, but they remain forever beyond our reach, not because of technological limitations, but because of the fundamental structure of spacetime itself. Paradoxically, this limitation is also what makes cosmology possible. Because light takes time to travel, we can look into the past by looking at distant objects. Telescopes become time machines, showing us galaxies as they were billions of years ago. The cosmic microwave background radiation gives us a snapshot of the universe when it was only 380,000 years old, when atoms first formed and the cosmos became transparent to light. All of this cosmic archaeology is possible because the speed of light is finite. If light travelled infinitely fast, we would only see the universe as it is now, with no window into its past. The cosmic speed limit doesn't just constrain motion and causality, it enables memory, allowing the universe to preserve and share its own history through the medium of electromagnetic radiation. This creates a profound connection between observers and the cosmos itself. Every photon that enters your eye is a messenger from the past, carrying information across space and time at the maximum possible speed. You are constantly receiving signals from across the universe, from different epochs in cosmic history, all travelling at this fundamental speed limit. The speed of light emerges as something far more than just the speed at which light travels. It's the rate at which reality itself unfolds, the tempo of existence, the fundamental rhythm that connects all events across space and time. It shapes matter and energy, space and time, cause and effect, knowledge and ignorance. It is, quite literally, one of the most important numbers in the universe, a constant that defines the very possibility of existence as we know it. And yet, for all its fundamental importance, it remains deeply mysterious. We can measure it with extraordinary precision. We can use it in countless calculations. We can observe its effects everywhere we look, but we still don't fully understand why it has the value it does, why the universe chose this particular speed has its fundamental limit. The speed of light stands as both one of the best-known constants in physics and one of its deepest mysteries, a reminder that even our most successful theories rest on foundations that we don't completely comprehend. In the end, the strangeness of the cosmic speed limit reflects the strangeness of existence itself. We live in a universe governed by mathematical relationships so precise and so universal that they seem almost magical. The speed of light is one thread in this cosmic tapestry, but it's a thread that connects to every other part of the pattern, influencing and being influenced by the deepest structures of reality. As you sit here now, photons are streaming through space at this cosmic speed limit, carrying energy and information from across the universe. Some have traveled for billions of years to reach your eyes. Others were created just moments ago by the device you're using to read these words. All of them move at exactly the same speed, the strange speed that nothing can exceed, the fundamental constant that shapes the very nature of existence itself. When we step back and consider all of this together, what emerges is a picture of the universe that is both elegant and unsettling. The speed of light isn't just a number that physicists have measured. It's a fundamental organizing principle that reaches into every corner of reality, from the smallest quantum interactions to the largest cosmic structures. It connects the behavior of individual particles to the fate of entire galaxies, links the flow of time to the structure of space, and bridges the gap between energy and mass in ways that continue to surprise us. But there's something even more profound hiding in this cosmic architecture. The speed of light doesn't just limit how fast things can move through space. It defines what space and time actually are. Without this constant, the concepts of distance and duration would lose their meaning. The universe wouldn't just be different, it might not be comprehensible at all. Consider how this plays out in the realm of quantum mechanics, where particles exist in states of probability rather than definite position and momentum. Even in this strange quantum world, where particles can tunnel through barriers and exist in multiple states simultaneously, the speed of light maintains its authority. Quantum field theory, our most successful description of fundamental particles and forces, is built on the foundation of special relativity. The speed of light constant appears in the equations that describe how quantum fields behave, how particles are created and destroyed, how forces are transmitted across empty space. This creates a fascinating tension in modern physics. Quantum mechanics seems to allow for instantaneous correlations across vast distances through entanglement, yet these correlations cannot be used to transmit information faster than light. The universe appears to have found a way to permit quantum strangeness while still preserving the cosmic speed limit. It's as if reality has built-in safeguards that prevent any violation of this fundamental boundary, no matter how exotic the circumstances. The more we probe these quantum effects, the more we realize that the speed of light isn't just about motion through space. It governs how information itself can flow through the universe. When physicists talk about information in this context, they mean something very specific. It's not just data or knowledge, but the fundamental capacity to distinguish between different states of reality. The speed of light sets the ultimate limit on how quickly the universe can process information about itself. This has implications that stretch far beyond physics. If consciousness depends on information processing, then the speed of light may set limits on the speed of thought itself. Not the speed at which neurons fire, which is much slower, but the fundamental rate at which information can flow through any physical system capable of computation. The cosmic speed limit becomes a constraint not just on motion and causality, but on awareness itself. But perhaps the most mysterious aspect of this speed limit is its relationship to the vacuum of space. We think of empty space as containing nothing, but modern physics reveals it to be seething with activity. Virtual particles pop into existence and annihilate each other in timeframes so brief that they can borrow energy from the quantum vacuum without violating conservation laws. These quantum fluctuations happen everywhere, all the time, creating a kind of quantum foam at the smallest scales of space-time. And so we come to the quiet end of our journey through the cosmic speed limit. This strange and beautiful constant that governs everything from the firing of neurons in your brain to the death of distant stars. The speed of light emerges not as a barrier, but as the fundamental rhythm of existence itself, the tempo that allows reality to unfold with meaning and order. It reminds us that the universe is far more mysterious and interconnected than we often imagine, governed by principles so deep that they shape the very possibility of consciousness contemplating its own existence. Sleep well, fellow traveller through space-time. Traveller through space-time.